Matthew Botvinick, ex-Princeton, now Google DeepMind, and he's going to talk to us about meta-learning in brains and machines, and I'm going to stick around until the screen works.
There we go. Okay, can you hear me? Yes, okay. Thanks, Matteo. And thanks to the organizers for inviting me. It's a fantastic meeting. I'm just honored to be a part of it. So yeah, I want to talk about brains and machines. Let's start with machines, though. So we'll shift gears here a little bit, and then we'll come back to brains as I go along. So like a lot of people here, I'm really excited about what's going on in AI. And I've been lucky enough for the past couple of years to be working at DeepMind, where I've had kind of a front row seat to some really amazing developments. Most of you be familiar, at least in passing, with a couple of things I'll mention just to get the ball rolling. This work with Atari from 2015, where deep reinforcement learning was used to get to superhuman level of play on these classic games. And then, in an effort to make that look quaint after 1 year, David Silver and his team developed AlphaGo. And then in an effort to make that look quaint, they took the same bit of machinery and applied it to chess and shogi. And so there are all these amazing things happening using deep reinforcement learning. These are cases that have been high profile enough that I think most people are aware of them. There's a lot of other stuff that I think people in the neuroscience sphere aren't aware of or don't know about in as much detail that I think may even in the long run be more exciting. So for example, the use of recurrent neural networks with deep reinforcement learning. So this is just a schematic. There should be a bunch of neuron-like elements here that are all connected to one another. So there are loops that give the system memory, and there's a conventional way of visualizing that is just to unfold the network in time. And you can train this kind of network with the same kind of deep reinforcement learning algorithms extended to the recurrent setting. And you can do things like navigate through mazes to find goals. This is literally the input that the network gets. So it's dealing with pixel level inputs, and it finds that kind of wavy goal and then respawns in a different part of the maze and then has to navigate to the location it discovered on the last trial. Just like amazing stuff. And this is all learned, it's all learned through reinforcement learning. It's not hand engineered. So I mean, I wouldn't be at DeepMind witnessing all these amazing things, though, if there weren't some tie-in to neuroscience, since that's at least a significant part of what interests me. And one thing I love about DeepMind is that the mission there is explicitly oriented around drawing inspiration, where possible, from neuroscience. And I worked with Demis Hassabis and Darsh Kumaran and Chris Summerfield on this Neuron paper, where we tried to lay out our philosophy about that. I encourage you to look at it if you're interested. But I think it's not just a question of neuroscience feeding into AI. I think there are also opportunities here for us as neuroscientists to draw new ideas from what's going on in AI. So that's what I want to talk about. So it's kind of obvious why what's going on in the research that I've just briefly mentioned might be relevant to neuroscience. It's, I think, evident from this single diagram from the Atari paper. This is a convolutional neural network. It's was originally inspired by biological research, and it's fed into recent research, for example, on the visual system from people like Dan Yeomans. So there's no need to argue that these kinds of artificial neural networks may have biological relevance. People are already taking that seriously. But there's these recurrent networks also have established connections with neurobiological analyses. Some of you may be familiar with this paper from a few years ago by Valerio Monti and David Cicillo, using rather vanilla recurrent networks to understand dynamics of working memory and prefrontal cortex, or more recent work from Francis Song with Jiajing Wang, doing something quite similar with reinforcement learning. And I also want to mention, for those of you who were here yesterday and heard David Heger's talk, he drew connections, very direct connections between LSTM networks, which we use a lot in the AI space, with possible working memory mechanisms in prefrontal cortex. So that's one side of it. Yeah, we're using neural networks, so we should pay attention to what's arising through learning in these networks as a source of hypotheses for what's going on in the brain. But the really exciting part to me is that this is being crossed with reinforcement learning. So the representation learning that's going on here is being driven by reinforcement learning. And for an audience like this, I probably don't have to go into much detail to explain that there is a biological tie-in. One of the biggest stories in neuroscience over the last 15 years has been this connection that's been made between temporal difference learning in computational reinforcement learning on the one hand, and dopaminergic function in the brain. I don't have time enough to review this. If you haven't heard about it, check it out. It's very important. We're just going to kind of use it as part of the background here. Okay, so that's my motivation for taking what's going on in the AI space and leveraging it to develop hypotheses about what's going on in human and animal brains. But having said that, it's also clear that the things that we're building in AI are not fully human-like. It's not like anybody at DeepMind isn't aware of that, but it's been very eloquently pointed out by Brendan Lake and Josh Tenenbaum and some of their colleagues in a recent BBS paper, at least one particular way in which the deep RL systems that I've mentioned are not human-like. And that is that they just require too much data. They learn too slowly. Okay, so the illustration that was provided by Brendan is, focuses on this Atari game called Frostbite. And down here you see a learning curve for DQN, which is the agent that was reported in that DeepMind Nature paper. And you can see it learns very slowly. It takes a lot of experience for it to get off the ground. Eventually it surpasses humans, but it takes a tremendous amount of data. And Brendan compares this with his own play. And it only takes him about 10 minutes to get up to a respectable level on Frostbite. And it's a little cheeky thing to do in an academic paper, but it's, the point is legitimate. The point is legitimate. So let's take this seriously. Why is Brendan good at this? Not only why is he good, but why is he good so fast? How is it that he's able to get up to speed on this new game with such a small amount of data? Oh, I just wanted to acknowledge that this is a win for NYU, yes. All right, so why? Well, because Brendan doesn't come to this game without background experience, right? Brendan has presumably played video games before, has dealt with computers before, has played other kinds of games before, knows something about igloos, perhaps. So there's a tremendous amount of background knowledge that can be brought to bear. Is that Brendan? Yeah, hi, Brendan. Revenge is sweet. But it's not just that. It's not just that. What makes him good, and what makes us all good at stuff like this, all jokes aside, is that we know how to learn. We come to new tasks with an ability, with a skill set for learning how to adapt. And this is a term that actually comes from psychology. It's been around since the 1940s. I use the term meta-learning in my title, same difference. What is learning to learn? Well, it was very vividly operationalized in the paper where the term was introduced back in the 40s by a guy named Harry Harlow. He did an experiment with macaque monkeys, and the idea was that he just put down two objects in front of the monkey, and he allowed the monkey to pick one up. And when the monkey did that, there was a well underneath, and the monkey found out whether it won a raisin or got nothing. And then a blind went down, and the same two objects were put down again. They could be in the same positions. They could be left, right, reversed. And blind went up. The monkey was allowed to choose again. After 6 trials with the same two objects, 2 totally new objects were introduced. And presumably these were objects that the monkey had never seen, and the whole procedure was repeated again. Now, importantly, there was a rule, which was for every pair of objects, there was one good object and one bad object, and the good object was always rewarded, the bad object was always not rewarded, and it didn't matter what left-right position they appeared in. And here's what Harlow observed. With each of the 6 trials with a particular pair of objects, the percentage of correct choices, that is the raisin choices, went up. But importantly, after a significant amount of experience with this paradigm, monkeys arrived at this pattern that's shown in light pink, which shows that they were at chance on their first choice. They had to be, because they couldn't know what was underneath the objects. But on the very next trial, they were at ceiling, whether they got rewarded or whether they didn't get rewarded. And Harlow pointed out that this indicates a form of learning to learn, because the monkeys had figured out how to infer the most that they could possibly infer about two new objects after one observation. They had learned how to learn about two new objects in the space in the setting of this task. Okay, so the question I want to address is, what do we have to add to these kinds of deep RL systems in order to see this kind of sample efficiency, this kind of flexibility, this kind of learning to learn? And the answer that I'm going to offer you is we don't have to add anything. These systems natively show learning to learn. They show it inherently. There's really nothing special that we have to do. And I'm going to try to convince you of that. There are two things that we have to do, but I hope you will find them totally uncontroversial. We probably should have been doing them all along anyway. One, we sometimes already do, which is that we need to use recurrent neural networks, because these kinds of networks have memory. Okay, so there's nothing unconventional about this. I'm just going to use recurrent networks for the rest of the talk. The other thing that's less conventional, but I hope you'll agree we should have been doing it all along, is rather than studying single tasks, we should study lots of tasks. We should train systems on many, many things and allow them to integrate across those many, many things in order to extract generalities, abstractions, concepts. Now, before I go on, I just want to mention that the ideas I'm going to be presenting are foreshadowed very strongly by this classic paper by Sepp Hochreiter, who, by the way, is the inventor of the LSTM. This group did not apply the insights in this paper to reinforcement learning, where the ramifications are quite different, but I do want to acknowledge that there's that background. I also want to say that those of you who are familiar with the relevant literature will recognize rich connections with a lot of the work that Kenji Doya has done over the years, so I want to acknowledge that connection. Okay, so let's get into some simulations. Now, for all of these simulations, I'm going to use a really stupidly simple neural network. It's even a little bit embarrassing to call it a deep network, because it only has one hidden layer. That's all we need for this proof of concept. And the idea is we've got inputs which represent some observation of the environment. That'll change from task to task. We have outputs which represent actions, usually coded in a one-hot manner, for those of you who are interested in that kind of detail. There are a couple of ancillary inputs and outputs that I'll mention, even though I don't think they'll be very controversial. One is that the network gets an input that indicates its action on the last time step. This is like corollary discharge. And the other, which is important, but I also think uncontroversial, is that the network gets an input to indicate that what reward it received on the last time step. And from Matteo's data, we know that the brain goes crazy when it gets a reward, so this hopefully shouldn't be too controversial. The other detail is that in addition to coding for the action output, the network's also going to put out a second signal that represents an estimate of the state value. How good is the situation that I'm in? For those of you who know about actor-critic architectures or reinforcement learning in general, you'll recognize this is a baseline for the reward prediction error. Okay, so I'm going to use this little loop to emphasize the important point that those units inside the network are all connected to one another, and therefore we have a recurrent network. And that gives the network memory, and it also gives it, critically, activation dynamics. So a pattern of activity will evolve over time in a way that's influenced by the inputs. And then finally, just to remind you, we're talking about deep reinforcement learning. This network is trained using a variety of the reinforced algorithms. So this is driven by reward prediction errors, very much like the ones that are discussed in the dopamine literature. And it's trained with backpropagation through time, so all of the weights in the network are trained in order to maximize reward. Okay, so let's start with the proof of concept, and then we'll pivot very quickly to neuroscience, because that's where I really want to get to. So this proof of concept is just a simple bandit problem. We're going to present the network with the opportunity to make a left or right action, and then it'll find out whether it got a reward, and then it'll move on to the next trial, left or right action. It'll find out whether it got a reward, and its job is to decide whether the left action is better or the right action is better, and there's some ground truth set of parameters that, that dictate the probability of a reward from the left and the probability of the reward from the right, standard two-arm bandit. But we're not going to stop there. When we've given the network a chance to learn about one bandit problem, we're going to give it another with a different set of parameters. And then we're going to give it another, and then we're going to give it another. We'll give it hundreds of bandit problems in a row. And we're going to backpropagate through a large enough window that it can really absorb what it learns about these tasks. Okay, now I'm going to show you what the network does after training, but there's one really important point, and if I don't get this across, then a lot of the rest that I'm going to say is not going to be clear. So during training, reinforcement learning is adjusting the connection weights. Think of it as synaptic learning, okay? At test, when we look at the performance of this network after it's trained, we are going to turn that off. There's no weight changes going on at all. Reinforcement learning is off, okay? And this is being done for rhetorical purposes, and you'll see why. So that's what that will mean. No more prediction errors changing connection weights. Okay, so what do we see? We give the network, after training on a bunch of bandit tasks, a new bandit task. We find that it explores and exploits. So it chooses left, it chooses right, switches around for a while until it decides that the right side is better. These are trials. These are bandit problems. These are actions within a bandit problem. That's what you see for a very easy bandit problem, where one arm is much better than the other. This is what you see for a harder bandit problem. And if you look in the aggregate at how well the network does in exploring efficiently and gradually transitioning to exploiting, pulling the better arm, it does pretty well compared to off-the-shelf optimal or near-optimal algorithms for bandit problems. So what's going on here? I said no weight changes, no synaptic changes. Reinforcement learning is off. So how is this network learning? It seems to be learning within each bandit problem. And the answer has to be that this is happening in the activation dynamics of the recurrent network. That's the only possible answer. And when we look inside the network at the patterns of activity as they evolve over time, in fact, we see very clear traces of what's going on. So in an easy bandit problem where the target is on the left, you see an evolution. So this is projecting a high-dimensional hidden state, activity state, a vector of activities into 2 dimensions, and you can see that the network's gradually deciding that the right answer, with each pull of the arm, it's deciding that the right answer is on the left. This is what happens when the answer is on the right. And when the problem's harder, sometimes you see it kind of go one way in hidden space and then reverse. So the important point that I want to make is that, again, there's no synaptic change. There are no weight changes going on in this network. What we see is a learning algorithm that is implemented in the activity dynamics. We're used to thinking of learning as involving synaptic change. Here we've got learning that's taking place just in the dynamics and the state of a recurrent neural network. So it's a very different way of viewing what learning is. Now, one cool thing about this learning algorithm is that it can be very different from the original learning algorithm that we brought to bear with the reinforced algorithm, the one that we used to change the weights. So imagine instead of the bandit setup that I just told you about, instead we make the parameters for the bandits anti-correlated across instances. So whatever that parameter is, that's going to be 1 minus that parameter. This is a much easier exploration problem because any information you get from one arm implies something about the other arm. And when we train this recurrent neural network setup on that, it actually shows much lower regret. It gets to the right answer much more quickly because it's learned to exploit this consistent structure. So this is the learning algorithm in the activity dynamics being fit to the structure of the domain. So it's learning to learn in a way that's very specific to the statistics of the environment. Okay, so now that we've got the basic idea in place, we can have fun with this. So can we explain the Harlow effect? Well, we set this up we pretended this was a video-based experiment. And in fact, the video I just showed you showed exactly what our network got. We put this through a convolutional neural network. We put pixel-based inputs through a convolutional neural network. And instead of objects, we used patches from ImageNet images. But again, every 6 trials, the network got image patches that it had never, ever seen before. These are totally novel. And what we find, again, testing the network without any weight changes going on, is that it showed an acquisition pattern and plateau behavior that looked very much like Harlow's animals. So once it had seen enough of these image pairs and gotten the rewards based on the structure of the task, then it was its ceiling after only 1 trial with a new pair of images. So learning to learn. Okay, good. So far I've been talking about machines, maybe about monkeys, but certainly not explicitly about brains. And now let's pivot to that. I don't have time to go into much detail, but I want to give you a flavor of the work that we've done on that side. And anybody who's interested in learning more, we have a preprint that I'd be happy to send you. So how do we connect this with neuroscience? Well, it's easy, actually, based on some of the pieces that I've already laid out. So it's not hard to argue that there's an analogy to be made between the reward prediction errors that are being used to train the weights in this network and phasic dopaminergic signals. Like, huge literature to motivate that idea. A little bit more innovative, sorry, I forgot I had that, is the idea that we can understand this recurrent neural network as capturing something at a very high level about the way that prefrontal circuits work. We've already heard this touched on in a number of ways in this meeting. It's actually quite common to model prefrontal dynamics using fairly undifferentiated recurrent neural networks. And we're going to take that step here too. So we're going to think of this mapping as we go forward. But other than that, our research strategy is going to be the same as it was before, but rather than modeling ordinary bandit tasks, we're going to model actual neuroscience tasks and look at neural correlates. Okay, so let's start with something that's very close to the bandit scenario, and that comes from a study by Sasui and colleagues. This is Wolf from Schultz's lab. It's a bandit problem. The monkey gets to choose between an A target and a B target, makes a saccade, finds out whether it gets a juice reward or not, moves on to the next trial, chooses again, and there are parameters that determine the payoff probabilities for A and B that stay constant for a while, and then they change. So it's very much like the bandit setup that we had before. The details of the task make it so that the optimal strategy is not to maximize, like constantly look at B, 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 but instead to probability match. That is indicated in the performance that the monkeys show. As you increase the probability of reward on one side, the monkey will look proportionately more at that side. It turns out now, if you train our recurrent neural network on exactly the training paradigm that they used in this experiment, and then test, again, without any weight changes, you see probability matching. So the statistics of the task here lead to probability matching. But again, we're testing without any weight changes. So the learning that's going on here, the adjustment to each new set of parameters, has to be driven by the dynamics, the activation dynamics of that recurrent network, which here we understand to relate to prefrontal cortex dynamics. Now we can test that, at least post hoc, by looking at the neurophysiology data that Sasui and colleagues also presented in this paper. They looked in dorsolateral PFC and found neurons that coded for the animal's choice on the present trial, the value of the estimated value of the stimulus that had been presented, and also, importantly, the history of actions and outcomes. It's critical to know that to do reinforcement learning. And this diagram just shows the proportion of units, the proportion of neurons that coded for those various things. And in fact, when we look inside our recurrent neural network, we find units that code for those same variables. In a way, it had to be this. This had to be our result. Otherwise, there'd be no way of understanding how our recurrent network is doing reinforcement learning. These are sort of the sufficient statistics that it needs to encode. But it's nice to see that correspondence between prefrontal cortex and our model, given our neurobiological interpretation. So a learning algorithm in the activity dynamics. Again, we're interpreting that in terms of prefrontal dynamics, but remember the story is that those dynamics are being trained up by dopamine under this story. Once that training is done, the prefrontal cortex circuit becomes autonomous in a way, but dopamine is shaping things in the first place. Now, I made a big deal earlier of the idea that this learning algorithm, which we're now saying lives in the prefrontal circuit, is fit to the structure of the task domain. So let me give you an example now that ties to neuroscience. So many of you will be admirers, as am I, of the study from Tim Barron's, where they looked at a bandit task where there were periods of stability, where the more rewarded choice stayed constant for a long time, and then periods of volatility where the best choice kept changing at high frequency. And if you are a fan, you'll recall that what the crux of the study was about learning rates. When things are stable, you want a low learning rate. When things are volatile, you want to bump up your learning rate because you want to wash out outdated information and let wash in new information in a rapid way. Well, we train our recurrent neural network on exactly this domain, and with a fixed learning rate on the reinforcement learning algorithm, I should mention. And in its behavior, you can see, if you infer its learning rate from its behavior with the weights fixed, you see that its learning rate changes in exactly the same way. The learning algorithm that the system has acquired is tailored to the structure of the domain in this way. And here that plays out at the level of learning rates. I'm going to skip that slide. OK. So I've mentioned a couple of simulations that focus on prefrontal cortex. Now let me briefly tell you about one of numerous. that focus instead on dopamine, because this framework can also explain some formerly mysterious things about dopamine. Perhaps some of you will know this excellent study by Ethan Bromberg-Martin. The idea here is the monkey sees a left target or a right target and has to saccade to it. There's no choice. The monkey just has to look at whichever one comes up. Critically, during some blocks, the left target is rewarded, and during other blocks, the right target is rewarded. And importantly, the monkey doesn't know when this is going to switch. The only way it learns that a reversal has occurred is by observing the reward outcomes. Bromberg-Martin and colleagues recorded phasic dopaminergic activity and found the following. So the blue curve here indicates a situation where, for example, the right stimulus has been rewarded over several trials, and then right is presented again. In that context, dopamine is happy. Dopamine signals a positive reward prediction error. Nothing surprising there. Sorry, excuse my wording. Now imagine that, in fact, the monkey is disappointed to find that the reward is withheld. That indicates that a reversal has occurred. Now, what happens on the very next trial? Well, if you present the right target again, you see a dip in dopamine. That's consistent with the classical story because that stimulus was just unrewarded on the previous trial. So maybe the system learned very quickly and now is disappointed or has a negative reward prediction error for that signal. The cool thing is what happens if right after the reversal, instead, the monkey is given the other stimulus. So the last time the monkey saw the stimulus, it was unrewarded. But if it understands the structure of the task, it can infer that it will now be rewarded. And in fact, that's what you see implied by the dopaminergic signals. You see a positive reward prediction error. And they refer to this as inferred value. So it turns out that if you just train a recurrent neural network on this task paradigm, freeze the weights, and test it on more of this task, you see qualitatively exactly the same pattern. Why? Well, when you look at the architecture, it's actually pretty obvious. The internal patterns of activity in the network, because they store information about history, are going to encode whether the task is in a left-rewarded or a right-rewarded state. Those activities are the basis for estimating state value. How good is this situation I'm in now? That state value is the basis for computing the reward prediction error, and therefore reward prediction errors are smart. It just happens emergently. No special machinery is required. Importantly, the neuroscientific gloss that we're making here suggests we had the arrow going from dopamine to the prefrontal cortex, training up prefrontal cortex. But here we see the opposite also implied. So patterns of activity in prefrontal cortex that represent latent states are also informing dopaminergic firing. And many of you will recognize that there's compelling evidence already that this sort of thing happens. OK, I have a couple of slides that I'm just going to dash past. I knew I wasn't going to have time for them, but I want people to be aware that we've done numerous other simulations that address seemingly very different phenomena in the neuroscience literature, including model-based control. For those of you who know, for example, Nathaniel Dawes' two-step task, this meta-learning setup provides an explanation for how model-based control can emerge out of model-free control. I don't have time to explain that, but if you're interested, come talk to me. We can also simulate the impact of optogenetic manipulations of dopamine. Again, come talk to me if you're interested. But I'll just wrap up now since I'm out of time. So we started with these amazing advances in deep reinforcement learning, which I argue we really should look at these as neuroscientists and decide what it all means. But of course, we also have to look at the ways in which these systems are not human-like and ask, what do we need to do in order to get them to be more human-like? And in asking that question about these deep RL systems, I offered the answer, nothing. These systems actually already show this kind of learning-to-learn behavior, assuming that you put them in the right kind of learning environment. And building on top of that computational observation, I've argued that it might shed light on the relations between prefrontal cortex and the dopaminergic system. What are we doing now? Well, obviously, we've only studied very simple tasks. It would be great to look at richer environments where richer abstractions can be acquired. We're looking at architectural biases. I don't want anybody to come away from this talk thinking that I believe that vanilla LSTMs explain all of cognition. I think we need architectural biases in order to shape learning. We're also interested in other forms of meta-learning, like architecture search, and Blaise mentioned some relevant techniques in his talk. And we're also getting interested in the role of episodic memory in recalling the results of earlier learning in a meta-learning system of this kind. And to close, I just want to acknowledge my collaborators on this, but especially Jane Wang and Zeb Kurth-Nelson, who actually did most of the modeling work. Thank you.
So we have time for a few questions. Can we just hold on if you've asked, but there's one right next to you, yep. So you could get to go first. When we're done answering questions, can you just, and we applaud one more time, can you stay in so I can make a couple of announcements?
This is so distracting. I'm seeing so many old friends. Hi, hi.
Yeah.
This is crazy.
Go.
Let's meet later. Yeah. Yes, question.
Awesome, wonderful work.
Thank you.
So, okay, cool. We don't need to add anything to get these kinds of emergent behaviors. But certainly, and this is kind of a follow-up on your point about architectural biases, certainly these behaviors will emerge from some architectures, but not others. What do you think the necessary and sufficient conditions for the emergence of these learning-to-learn behaviors might be?
Well, I mean, there has to be enough data to allow learning to hone in on the right abstractions, right? So what I mean by the right abstractions is, in the Harlow task, the system had to infer at some implicit level in its weights and dynamics that there's a good thing and a bad thing, and it doesn't matter which side they're on. So there has to be enough data in order to keep the system from overfitting and developing strange, superstitions, right? Now, ironically, that might put us back in the same position that Brendan was inveighing against. It's a very data-hungry, it's fine in these tasks that I've been talking about because the tasks are so simple, it doesn't take that much data to really force the system to form the right abstractions. But, what about video games, right? What about Frostbite? How much data would you really need? I joked that, oh, well, Brendan came to the computer with all sorts of past experience. But how much past experience would you really need in order to have the right biases to quickly learn about Frostbite? And that may be prohibitive. So I think there are two ways of easing that concern. One is to appeal to evolution. Right? From a biological point of view, this evolution is a learning process too, and it involves meta-learning. I'm not the first to point that out. So in fact, it's not just how much experience Brendan's had, but it's how much experience all of his ancestors have had. That helps, right? From an AI point of view, though, we can't recreate evolution, and therefore we need to resort to, I think, what you have in mind, which is architectural biases. So one thing that I'm very interested in, as are many of my colleagues, including Brendan and Josh, is the fact that the world is, coarsely speaking, made up of objects that have relations. And if we have systems that are biased toward carving things up in that way, that might really help, right? That way, it means that the system, is biased to thinking that the igloo is a thing, right? And the ice floe is a thing, and that really should help things get off the ground and prevent overfitting. Fortunately, we're making progress on that sort of thing. So Peter Battalion, my group at DeepMind, has been built, and David Raposo, who I think has connections historically with other people here.
Yeah.
Yeah. Okay, yeah, there you are. Are doing great work in this space.
We have quite a few people lined up.
Sorry,
so can I ask for quick questions, if possible?
And
one over there,
answers.
and then we'll go over there, and then we'll come back here.
Sure. So in your network task, the learning to learn is really learning to behave in the absence of plasticity, right? And I'm wondering how far you think you can push that to, say, the more harder tasks like the Atari example, as opposed to actually allowing prior learning to drive new plasticity. How far do you think we can go in this first regime where you're learning to generalize behavior without actually do what I would call learning to learn, learning to adjust the plasticity?
Well, I'm not sure I understand the question. So let me answer. Let me tweak the question a little bit so I can give a meaningful answer. I think it's fair to ask, how far can you push this, right? So we've just been talking about that from one perspective. Another limitation has to do with timescales, right? So we're using backpropagation through time, which is admittedly biologically not plausible, and it also sets a limit on how far back the experiences how far back in time we can go before we lose the ability for past experiences to influence our current behavior or our current learning. So we just need better methods for temporal credit assignment. And I don't have them. I want them, and if anybody comes up with them, I hope they'll tell me. But AI needs those too. One other thing I'll mention, though, because it's a glaring limitation of what we've done so far, is that this system is kind of like an amnesic patient. So it can handle a new bandit problem, but the minute that that bandit moves out of its focus of attention, so to speak, and it moves on to another bandit, it just forgets that bandit. All it retains is general principles. It learns about bandits and how to solve them. So imagine you had a bandit problem where each bandit had a picture on it, like, you know, the Eiffel Tower was on one and a lion was on another. So now you get the Eiffel Tower one and you try it out and you say, oh, the right arm's the better one. And then you move on to the lion. And then sometime later, the Eiffel Tower one comes back. Now a human, within some reasonable set of parameters, would go, oh yeah, I've seen that one before. I think, yeah, it was the right arm that was better. Right? This system does not do that at all, I actually believe an amnesic patient would probably show, like a hippocampal amnesic patient would likely show that behavior, so it's kind of interesting. And in that spirit, we're doing work now that augmenting the system with something like an episodic memory that retrieves latent states when cued by, but that is a limitation of the current system.
Okay, so we have now a question there, and then we'll come back to that aisle. There you go.
So really great talk.
Thank you.
In looking at the network that was able to do the repeated bandit problem, it seems interesting that it was able to learn without changing weights at all. And looking at the sort of low-dimensional activity, it kind of looked like it was doing evidence integration,
yep.
But clearly something more complicated is going on than that. Could you maybe provide a little intuition to connect evidence integration to what it's actually doing?
I don't think it is any more complicated than evidence integration.
So there's kind of like a generalized thing where it's able to just say, okay, option 1 and option 2, and
So when I was first working on this, I was talking a lot with Andy Bartow, who some of you will know is one of the pioneers of reinforcement learning. And once I explained the idea to him, he pointed me to this very old literature on something called learning automata, which are basically finite state automata in which the states of the system are kind of belief states. And you can use these to model decision-making bandit tasks, for example. And you can think about them as doing inference, right? They're doing evidence integration. So I don't think of this as any different. When I first described this work to Alex Pouget, he said, is this network doing inference or is it doing learning? And I said, I dare you to tell me the difference. So I really think in the end it's all one big thing. The cool thing is that it's doing evidence integration in a learned fashion. Right? So it's fine to build a system that can do evidence integration in dot motion task, and you furnish it with the likelihood function. You furnish it with the right priors. Right? It's another thing to have a system that just figures out what the right hypothesis space is and the right update function, what those things are for a particular task, and that can be trained in different environments and arrive at different conclusions. So this is a system that can be put in the Harlow task and figure out that the way that it does evidence integration is to figure out which is the good thing and which is the bad thing. You put it in Tim Barron's task and it figures out what it has to infer is what the right learning rate is, and so forth and so on. So that's what excites me about it, is that it's a system that learns to do evidence integration in a domain, a way that's suited to the training domain.
Okay, so we're going to have two questions there, Joshua, and then behind, but if we can keep it kind of tight.
Well, I think you've already answered a lot of my questions, but regarding the fact that you're storing information in the activations, which normally in a real brain would be stored in weights, have you considered actually backpropagating through the storage through weights, which is, of course, another thing that people doing learning to learn are doing, and actually had a paper in '91 with my brother doing this kind of thing. And you can backprop through time again. Have you considered these kinds of approaches? So
we're considering, well, so you're referring, I think, in part to the recent mammal approach. Do I have that right? You backpropagate to get a you backpropagate through backprop, essentially, right, in order to get a set of good initial weights.
It's not backprop to backprop, it's backprop through whatever update rule you choose. Right?
Okay, fine, yes.
Which is learned.
Yes. So I think all of these possibilities are...
Because in a real brain, of course, we don't store these kinds of information in activations except for a very short period.
Yes,
and
okay.
Your thing is learning over, I don't know, hundreds or thousands of trials.
That's right. So our approach in this line of work is to say, yes, this information is, in fact, lost at the level of activities we believe that in humans and other animals it can be retrieved. How could it possibly be retrieved? And our answer there is episodic memory, for which we're using like a differentiable neural dictionary, right? So that's our approach here. There are other approaches that, that don't have that problem of things being thrown away. On the other hand, approaches like mammal, to me, feel like they don't capture exactly the same scenario because they seem to address a problem where you want to initialize the system so that it can learn, so that it can differentiate, right? So the way I think of it is, oh, you're not talking about that, okay. Well, so let me leave it there, but I'd love to talk with you more and get a better sense of what you're referring to.
We have now time for one more question.
Okay, one more.
Yes.
Hi, Ida.
So awesome work as always.
Thank you.
So I'm wondering, what do you think are the representations in the hidden layers that allow for learning to learn? Alberta people would talk about eigenoptions. Some people would talk about basis sets. One of the good successes of ConvNets was to compare with RSA to different layers of the visual cortex and the ventral stream. What is the equivalent of that for the prefrontal cortex? Is it eigenoptions at the end of the day? Is it some kind of and are you guys doing something towards that, towards the hierarchical sort of, is it sub-goal representations?
We're very interested in this. I think the answer is going to be different. The answer is going to be domain specific, right? Because the only generic way of talking about what the system is doing is that it's doing latent state inference, right? But what are the latent states? And I focused on tasks here where the latent states are obvious. By design, like people designed these neuroscience experiments because it was clear what you should go looking for. That was the right thing to do. But now we're in a position as a program of research to take this system into domains where we're not sure what the right abstract representations are, and to see what the network comes up with. It's challenging. So I will say that we were really excited when we got the Harlow effect, and we thought, well, let's go in and see what the thing's doing. But because every picture that it's seeing is completely new, it's actually hard to back out the abstractions. It's hard to figure out exactly how this network is doing what it's doing. So there's a challenge there. I mean, anybody who does analysis of deep learning systems knows that it's just as hard as doing neuroscience. It's not just having access to all the parameters does not solve the insight problem.
Maybe that could be your last.
Well, let me just say one more thing,
because it is a good last.
Yeah, I just want to add one more thing. I'm sorry. So one problem that we have in pushing this line of research forward is that the representations that we get here, the abstractions that we get, are only as interesting as the task domain, right? So it's easy to build bandit tasks. What we want to do, and what we're trying to do now, is write code that can generate procedurally generate very, very diverse video games, so that the system is then the abstractions the system then has to learn are things like, yeah, there's such a thing as an avatar, there's such a thing as a creature that's going to eat me, but it has to instantiate these notions in very different ways across games. That's the environment design thing is a very, very challenging part of this. Thank you.
Okay, so on that, thank you so much, and.